Hello everyone, my name is Dr. Moksha Satya. I am an assistant professor in Aditya Silveroak Institute of Technology, Silveroak University. Today I am going to start with the topic of mathematics, that is matrices, which is in semester 1. So matrices are very important in engineering as they give a concise and powerful mathematic framework to represent and solve wide range of complex problems in various engineering disciplines. So in short, matrices forms a column and row-wise representation which can be useful to solve difficult problems which are arising in engineering disciplines. Today, I am going to cover basic one, that is the definition of mathematics and types of mathematics, kind of row matrix, column matrix, zero matrix, identity matrix, diagonal matrix, square matrix, and many more. So let's start with the definition of matrix. It is a set of mn elements where elements can be real and complex which are arranged in a rectangle array of m rows and n columns. This is called a matrix of order m by n and written as m cross n. An usual mathematics representation in a form of like this, where first row is a11, a12 and going to the last element of row 1 is a1n. Similarly, for a second row a21, a22 up to a2n. And if we go on like this, we'll reach to the last row which is AM1, AM2, AMN. Where here A11, A12 where 1, we can see this 1 represent the number of row and this 1, 1 means the second one is the number of column. So in short, a matrix element can be represented as Aij and with that we have a whole matrix representation as like A is equals to Aij by m cross n. Now in an element Aij is the element of ith row and jth column. That means in this I represent the number of row and j represent number of column. So the element of matrix also can be represented ijth element of a matrix. So now let's start with the type of matrix. The first one and the basic one is a row matrix. Matrix having only one row and any number of columns is called a row matrix. Here we have a restricted number of rows, that is we can only have one row, but we don't have any restriction on a number of columns, so we can have any number of columns. Now let's take 2, 5, minus 3 and 4 in a row manner, so it will create a row matrix. Next start is a column matrix. Similar, the way we have seen in a row matrix, we have a column matrix. In this matrix, we have only one column and we can take any number of columns which forms a column matrix. Now, for column matrix, let's take 1, minus 3, 4 and 0 and rearrange in a column manner. It will create a column matrix. Next is a zero matrix. Zero matrix itself defines its identity that the matrix only having zero number is called a zero matrix. So let's see. A matrix whose all elements are zero is called a zero or a null matrix. Now, if we have all the matrices as a zero, then we can denote it as a zero. So its denotation is a zero. Here, we don't have any restriction on number of rows and number of columns. We can take any number of rows and any number of columns to make a zero matrix. Next is a square matrix. Square means a rectangle which have a size, same size of their sides. In here also we have equal number of rows and columns. So in a matrix in which the number of rows is equal to the number of columns is called a square matrix. Now let's take a look to the example. First example is 2, 3, 1, 4, which creates 2 by 2 matrix. That means we have number of number of columns and 2 rows. In a first row we have 2, 3, and in a second row we have 1, 4, which forms a 2 by 2 matrix. For the second example we have 3 by 3 matrix, which is 1, 3, 2, minus 1, 4, minus 5, 2, 6 and 8. The next one is diagonal matrix. For the diagonal matrix, we have one condition that the matrix should be the square matrix. Means a square matrix whose all non-diagonal elements are 0 and at least one diagonal element is non-zero is called a diagonal matrix. For example, we have 2 cross 2 matrix and 3 cross 3 matrix. You can see in the both matrices we have only the entry which are in a diagonal one are non-zero, otherwise every element other than a diagonal one are zero, which makes a diagonal matrix. The next one is identity matrix, or we can say a unit matrix. For this also we have a square matrix. In precisely we have a diagonal matrix. Means a diagonal matrix whose all diagonal elements are unity. Unity means 1 is called a unit matrix or an identity matrix. It is denoted by capital I. For example, we have 2 cross 2 matrix and 3 cross 3 matrix. First one is 1001. We can also denote it by I2 because it is a 2 cross 2 matrix. And the second one is 3 cross 3 matrix, means order of 3 matrix. That means we and I denoted with the I3 one, which is 100, 010 and 001. The next one is a scalar matrix. Scalar one is a kind of a unit matrix, but there is a slight difference between both the matrix. That is, in a unit matrix we have a diagonal entry as a 1, but in a scalar matrix we can have any one, but all of them should be same. Means a diagonal matrix whose all diagonal elements are equal is called a scalar matrix. For example, we have 3 0 0 3 minus 2 0 0 0 minus 2 0 0 0 minus 2. In both example you can see we have only a diagonal elements which are non-zero and the elements are equal. So it makes a scalar matrix. Next is a upper triangular matrix. A square matrix in which all elements below the diagonal are 0 is called an upper triangular matrix. Means we need to take a diagonal one, and if we have zeros in a below diagonal is called upper triangular matrix. For example, you can see 1 3 2 0 4 minus 5 and 0 0 8. Here a diagonal matrix means a diagonal entries are 1 4 8 and below that each and every element are 0. Same manner a lower triangular matrix. A square matrix in which all elements above the diagonal are 0 is called a lower triangular matrix. For example, 1 0 0 minus 4 0 2 6 and 8. Here diagonal entries are 1 4 and 8. Now according to these entries, if we go up in a diagonal in a transition mode, we can see all the elements are 0, and that's why it is called a lower triangular matrix. Now, next is a trace of matrix. The sum of all diagonal elements of a square matrix is called a trace of matrix. That means we need to have a one matrix which should be a square matrix. Now we need to pick up elements which are in a diagonal one. So in this matrix we have a 2, 6 and 3 in a diagonal one. So if we sum all these 3 elements will have a trace of matrix. As for example, 2 plus 6 plus 3 is 11. That means the trace of this matrix A is 11. Next is a transpose of matrix. A matrix obtained by interchanging rows and columns of a matrix is called a transpose of a matrix. It is denoted by A dash or A T, means A transpose. For example, let's take a matrix 2, minus 1, 0, 4, 6, minus 2, minus 1, 0 and 3. Now let's convert its first row in its first column. For example, here 2 minus 1 and 0, we have arranged it in a column manner, which is like this. For a second row, 4, 6, minus 2 is arranged in a second column, 4, 6 and minus 2, and the last row is arranged in a last column. So we have a matrix A, and now we have a matrix A transpose, which is 2, 4, minus 1, minus 1, 6, 0, 0, minus 2 and 3. Next one is a symmetric matrix. A square matrix A equals to Aij, means n cross n, is called a symmetric if Aij equals to Aji for all ij. In a different manner or in a simpler form, if I can say, if I transpose my matrix and the main matrix and the transpose matrix are same, that means A equals to A transpose, then the matrix is called symmetric matrix. For example, 2, 4, 4, 3. If I give a transpose to 2, 4, 4, 3, it will give me 2, 4, 4, 3 only, and that's why it is a symmetric matrix. Same way in this, we have a complex entries also. 1, I minus 3I, I minus 2, 4, minus 3I, 4, 3. If we give a transpose to this, it is also it will be the same one. Now next is skew symmetrics. Skew symmetrics matrix. A square matrix Aij M by n is called a skew symmetric matrix if Aij equals to minus Aji for all ij. That means if I have a matrix A and if I give a transpose of the matrix and a sign is different, means A equals to minus A transpose, then we have a matrix is called a skew symmetric matrix. But in this matrix, the diagonal elements should be 0. Okay? Because there is only one number 0 which is equals, which if we apply a minus sign, it will remain same. So for example, we can say 0 minus 3i minus 4, 3i 0 8, 4 minus 8 and 0. Next is a orthogonal matrix. A square matrix is called orthogonal if A into A transpose is I. Means we need to multiply a matrix A with its transpose and it gives you the identity matrix of the same order. It will called a orthogonal matrix. Next is a determinant of matrix. For this, let's take a matrix A, which should be a square matrix. So it is important. If we do not have a square matrix, we could not find a determinant of matrix. Now, a determinant of matrix is represented as mode A. For this, let's take a matrix A, 2, 3, 1, 1, 2, 3, and 1, 1, 0. And the determinant of matrix is determinant of 2, 3, 1, 1, 2, 3, and 1, 1, 0. Means a determinant of matrix gives the value of a matrix. Next is singular and a non-singular matrices. A square matrix A is called singular if a determinant of A is 0 and non-singular if determinant of A is not 0. So, singularity of matrix dependent upon the determinant of matrix, that means a value of matrix. If a matrix value is 0, it is a it is a singular matrix. It is non-zero, it is a non-singular matrix. Next is the minor of an element of a determinant. From this you can see we can find minor of an element not for the whole matrix. For this minor we should have a determinant. So let's take a determinant of A. Here I have taken A in a general form, which is A11, A12, A13, A21, A22, A23 and A31, A32, A33. Means I have taken 3 cross 3 means order of 3 matrix, and the minor of an element of a determinant obtained by leaving the row and column passing through that element. So if we want to find a minor of any element, we should eliminate a row and a column which is passing through it. So for example, if I want to find a minor of A11, I should skip, means I should eliminate first row and first column. Now I will be resultant with the 2 by 2 matrix, which is A22, A23, A32 and A33. And finding out the determinant of this, I will have the minor of this element. So this minor is not only for limited to one element. I can find minor of each and every element. For example, I can also find a minor of A32. Now element A32 is an element of row 3 and column 2. So for this minor of this element A32, I need to eliminate row 3 and column 2, and the resultant matrix will be of order 2, which will be A11, A13, A21 and A23. Next is a cofactor of an element of a determinant. So once again, for each and every element, I can find a cofactor, and for that I need a determinant. So once again, I am taking the same example, same matrix of order 3 which I have taken for a minor. So for cofactor of an element of Aij of a determinant is a minor multiplied by minus 1 raised to I plus j. So for example, I want to find out the cofactor of A11. So first of all, I will need a minor of that, which is A22, A23, A32 and A33. Now I need to multiply this minor with the minus 1 raised to the number of that element A11 and plus the number of column of that element, means 1 plus 1. This element is of a first row, first column. So I need to multiply my minor with minus 1 raised to 1 plus 1, which is positive 1. Next, the cofactor of the element of A32. So I need to find out the minor, which is A11, A13, A21, A23, and need to multiply it with minus 1 raised to 3 plus 2. Using this, I will have to find the inverse of matrix. If A is a square matrix and the determinant of A is non-zero, and if A into A inverse is equals to I, which is equals to A inverse is equals to A, where A inverse is called the inverse of a matrix A. That means if I have a matrix A and its inverse is A inverse, means A raised to minus 1. If I multiply both of them and I am finding identity, in the end, I have the inverse of a matrix, which is A raised to minus 1. Now, next is elementary row operations in a matrix. This is very important one for this semester 1. In this, we have different operations, row operations for the matrix, which will convert a matrix in a different form, which will help to solve the example. The first operation is interchanging any two rows. Means for this operation we can have interchanging of first row and third row. Means in a place of first row we can write a third row, and a third row in a place of third row we can write a first row. And the notation of this is Rij. The second operation is the multiplication of the element of any row by any non-zero number. Means we can pick up any row and we can multiply any non-zero numbers to that row, and that is our second operation. Last but not the least, the third operation, the addition or a subtraction of k items, the element of a row to corresponding element of another row where k is non-zero. So in short, in this operation we can multiply any row. Means say jth row, we can multiply jth row with any non-zero number k, and I can add or subtract it from ith row. Means the notation will be Ri plus or minus k Rj. These row operations can be useful to identify inverse, to find the solution, to find many more things. So these are the very important one. These three operations: interchanging row, multiplication to a row, and addition or subtraction of multiplication of any rows to the another row. Now the question is, if we apply this operations to a matrix, do it change, means does it change its identity, its property? For this we have elementary matrices. A matrix obtained from a unit matrix by subjecting it to the row transformation is called an elementary matrix. Means the resultant matrix which will be obtained through having the row operations is called the elementary matrices. But the question remains the same. Do we change the matrix property by using row operations? And the answer is equivalence of matrices. Means if B win an m by n matrix obtained from an m by n matrix by elementary transformation of A is called equivalent to B. Means let's take matrix A and the order of matrix is m by n. Okay. Now we have applied many rows and operations, and we have ended up with the matrix B. Okay. But obvious is a matrix A, it will be not equal to the matrix B. But we can say the both matrices are equivalent, and the equivalent terms itself defines we will not changing its property. So in a symbolically manner we can write A equivalent to B like this. So in this lecture we have seen a matrix means a representation of rows and column, means array of rows and column arranging n elements of n rows and n columns, or vice versa, and the type of the matrices, and the equivalence of matrix which can be obtained using row operations, three row operations, and which will not change the properties of the matrix. So for today, thank you.